Okay, this is the review for Unit 7. An experiment to test the effectiveness of regular treatments with fluoride varnish to reduce tooth decay involved 36 volunteers who had half their teeth, the right side or left side determined by a coin flip, painted with a fluoride varnish every 6 months for 5 years. That would be weird if you had different colored teeth on each side. I don't know if that would make a difference. At the end of the treatments, the number of new cavities during the treatment period was compared on treatment, fluoride varnish, side versus control, no fluoride varnish. The appropriate statistical test for analyzing the results of the experiment is, okay, so they're testing, both sides of the thing. So it's not one of the one samples, right? It's definitely not about proportions. But so really you're debating, is it a two sample or is it paired? And it seems like you're pairing with yourself, right? You've got half your teeth, the left half or the right half is that one. So it's definitely paired data. So I think that would be C. Has the large sample condition been met for these situations here? So this one's skewed right, and the N is 28, which is too small, and it seems to be skewed right pretty majorly. So I'd say no, maybe for that one. This one, I'd say yes, even though it's skewed right, N is more than 100, so it seems like 2 only would work there. Random sample of 68 workers from Company 1. The mean number of sick days taken in the previous year was 4.8 days with a standard deviation of 2.1. In a separate random sample of 34 employees, Company 2, the mean number of sick days taken in the previous year was 2.5 days with a standard deviation of 1.1 day. Calculate, interpret the standard error. So I think the formula for this type, I'm spitballing here, but I think this would be it. So it'd be standard deviation squared over sample size plus standard deviation squared over the sample size. So it would be 2.1 squared over, that was 68. And then standard deviation was 1.1. And that was a sample size 34. So I think you would get your calculator out and maybe do that one. Let's see if we get one of these numbers. It's a good question. Oops. Okay, control this one. So inside of there, we're going to do a fraction. So 2.1 squared over 68 plus 1.1 squared over 34. And we get 0.317. Okay, so 0.317, so it's one of these guys. Okay. So typical variation from the true mean difference of 2.3 is about 0.317 days. It's not terrible definition there. It's really basic. I'd wanted to say, I believe in repeated random samples or random samples of those sizes, which D looks better in that case. I'm leaning towards D here. The typical distance between the sample mean from Company 1 and the sample, well, that's definitely, it's not going from sample mean to sample mean. That's just silliness. We don't know what the true mean is, but it's the typical distance away from the true mean for the samples would be, sorry, I think it's D. It is D, I'm pretty sure. That's a tough one. For a study of the impact of caffeine consumption on reaction time was designed to correct for the impact of the subject's prior sleep deprivation by dividing 24 subjects into 12 pairs on the basis of average hours of sleep they had the previous 5 nights. That is, the 2 with the highest average sleep were paired. Okay, so they were paired data. So then the 2 with the next highest, etc. One randomly selected member of each pair was allowed to drink 2 cups of caffeinated coffee. The other drank 2 cups of decaf. each subject's performance on a standard reaction time test was recorded. This is interesting. Which of the following is the correct check for the large sample condition? Oh, so they don't tell me there's also an experiment. I just wanted to see what happened there. So what do I have to do? Okay, the scores of the caffeine drinkers and the scores. So we don't have to check each one individually there. That's definitely not true. It's paired data. It's all about the diff. Scores of caffeine drinkers and the scores in the study and the difference, no. The differences could have come. I'm leaning towards C. Confirm that at least one of the individuals. No, that's definitely not it. It's paired with all of the difference because essential limit applies. Not necessary to check any of the samples for normality. 24 and 12, no, CLT doesn't apply, so it's got to be C. Okay, this is kind of a fun one. Okay, so just pretty straightforward here. So 0.99, so there's 0.005 over here, so you can go inverse T, 0.995. Comma, degrees of freedom 19, and you're going to type that in your calculator. And when you do that, well, let's see, to get there, it's been a while. Menu 6, 5, I'm guessing, inverse T is 6, area 0.995, and degrees of freedom 19. It's 2.86, 2.86. There you go. Researchers wish to test the effect of additional extra calcium to yogurt and the tastiness of the yogurt. 62 adult volunteers were randomly divided into two groups of 31 subjects each. Group 1 tasted the yogurt. So this is definitely not paired data. I just got two groups of 31. Both rated the flavor on scale from 1 to 10. The ratings for the group 1 was 6.5, standard deviation of 1.5, and 7, standard deviation of 2. Let those represent the mean ratings you observe. Okay, so I like to kind of compare. These are all the same, right? So I'm not going to worry about that. Okay, so there is a different value there for the two critical values. So let's look at that first, maybe. So let's see, 90%. So this is 0.9. So this is 0.05. So we're going to go inverse T. I think we're talking about means 0.995, comma 29, I believe, right? Wait, it was 30. Sorry, 31. So this would be 30. So let's do that first. So 0.95. Why did I say 0.995? 0.95. So 0.95, comma 30. 1.697. 1.697. One of these guys. Okay, I like that. Those guys are gone. Let's see, what's the difference between those? Oh, it's definitely N. It's got to be D, I believe. That seems to be right. Yes. So sometimes it just helps to compare. That time you knew the formula. You didn't have to really look it up. You could just compare the different ones and decide. Suppose we were testing the null hypothesis. Use 50 against the alternative that's not equal to 50. That's two-sided. Approximately normal population, random sample of 9 observations are drawn for the population. Sample mean is 53, standard deviation of that, which is following it contains the p-interval for the test. Okay, so null's 50. Okay, so this is pretty tough. So this is 50. The standard deviation of x bar is going to equal to, the formula is standard deviation is 6.48 divided by square root of n, which in this case would be square root of 9. So that's going to be your standard deviation, whatever that is. Somewhere over here is 53. You're shading this way, but it's also a two-sided because the alternate is this. So you have to shade this way. You have to double that p-value you get from doing norm CDF. So I need to do that standard deviation first, I think, to get this. I want to get this right. So 6.48 divided by square root of 9. I'm just going to put 3 in there because it's square root of 9. Is 2.16. Okay, so now I'm going to do my TCDF, right? So menu 65 TCDF, and the lower bound's 53. Upper bound's infinity, which is a big number there. Degrees of freedom. Okay, so I was going to use that and I was like, something's wrong. I was thinking norm CDF, kind of thinking we need to find T first. So we're going to use those values we just did. So it'd be X bar, which is 53, minus the mu, which is 50, over, I'm just going to use 2.16, but it'd be standard deviation divided by square root of 9. We just did that, so I'm going to use what we just should. So let's figure out what our T is for this one. So we're going to do the fraction 53 minus 50 up top over 2.16. I think that was exact. So our T is 1.39. Okay, so now let's do our TCDF. I believe we can do this. Boy, this one, again, a little bit on the tougher side. Okay, TCDF. Okay, so 1.39. Upper bound, infinity. Degrees of freedom was, there were 9 observations, so it's 8. And you get that number. Now we have to do 2 times that value because it's a two-sided test. So we get 20%. So p-value is 20%. Let's see where that fits. More, it's 20-some%. So it's actually should be. Let me just double check that one. Yeah, it should be. So yeah, it'd be really easy to forget and get, it's just a little over 10% there, but it's just a little bit over 20 because it's two-sided. Okay, which of the following actions will increase the power of a one-tailed t-test for me? Okay, so increase the sample size. For sure, that one. So just real quickly, it's really good to know this one. This is reject. This is fail to reject. This is null is true. This is alternate is true. So this is type 1. This is type 2 error. Those are incorrect decisions. Power is correctly rejecting the null. So if you want to have a better chance of rejecting the null, the power is going to be higher. That's your chance of correctly rejecting the null. And there's a relationship between these two. Power and type 2 have a complementary relationship. In other words, let's say type 2 is 20%. This would be 80%, or 1 minus 0.2 would be 80% there. So those two are related, type 2 and power. If this type 2 was 30%, power would be 70%, et cetera. So keep that in mind. I know that's from last unit, really, but sometimes, stats kind of builds on itself, so there might be a question about that. Mean time it takes for a person to experience pain relief from aspirin is 25 minutes. A new ingredient is added to help speed up relief. Let mu the true mean time of pain relief for the new product. An experiment is conducted to verify the new product. What are the null and alternate? So I didn't really read those, but those are probably not it. So because of the null is just, it's 25. There's nothing going on here, right? Experiments verify whether the new product works more quickly. So we want it to work more quickly with the new product. So we think that the time is going to go down. So I think that would be B. That's not too bad a question there. I like that one. The Excellent Drug Company claims its aspirin tablets will relieve headaches faster than any other one on the market. To determine whether Excellent's claim is valid, 30 volunteers are suffering from headaches are randomly assigned to two groups. Subject in one of the groups are given Excellent's aspirin, the other one are given aspirin from, so it's not placebo, but it's just a different drug company, the Simple Drug Company. They're very humble. The number of minutes required for each subject to recover from the headache is recorded. Test is performed using 5% for alpha, determine whether it's significantly faster in Simple's. Data was analyzed with Minitab. Here's the results. Okay. So it doesn't seem like the data was paired. Well, let's see. Where maybe they were. Let me think about that. 30 volunteers. So 15 and 15. They didn't pair them up in any way. It didn't talk about. So I think this is two sample for means, two sample t-test for the difference in means. If the company performs a test committed a type 2 error, which is fine, describes what could have happened. So type 2, I'm thinking generically, that means they failed to reject. So they didn't think the drug was, the Excellent drug was effective, but actually it was effective, right? So company concluded that works faster. No. Company hasn't concluded works faster when it really does. Boy, I'm heavily leaning towards B right now. Company concluded that aspirin works faster than Simple when it does. Well, when it does, it's funny. Company rejected the null. No. Company failed to reject when p-value was less than alpha. No, that's not the kind of error we're talking about here. That's just, not knowing how to do stats there. Errors happen when you use stats, but not that kind of error. Okay, so for years, Alex kept careful records of the time it takes to commute from his home to a place of work. On average, it takes him 28.4 minutes to travel from home to work. Torrent Transportation recently installed 2 additional traffic lights along Alex's route, and Alex is concerned the new lights will change the average commute time. I think it will. Alex records the home-to-time travel for 12 days. Mean is 32.2, standard deviation of that, etc. So expected data shows no skewness or serious departures from normality. Construct and interpret a 95% confidence interval for the mean home-to-work travel along the route. So mu is Alex's true mean home-to-work commute time along the modified route there. 99% confidence level. I guess you should say that 99% is the confidence level. Okay, so this is called a one sample t interval. For the means. And we're to check the conditions. So is this an experiment or not? Looks like a random sample of 12 days. Random sample of 12 days. 12 is less than 10% of the population of all possible home to work commute times. And so this one, so the sample, let's see, sample size is not big enough. I don't think we know about the population. We usually don't. So do we have a picture of the data? We really don't, right? It helps to read the last line. Here's where it says, so it just tells us the data shows no skewness or serious departures from normality. In other words, it's roughly symmetric or there's no major skewness there. So, you're referring to that when you say you paired that back into the question there. Okay, good idea to show your work if you can here. So 30. So X bar would be 30.2 plus or minus. To figure out the T critical value there, so you're going to do, this is 95%, so 0.95, so 0.025, so inverse T, 0.975, comma, gets a sample size of 12, so degrees of freedom is 11, and that should give you something around 2.201 when you type in your calculator. And I think this is just standard deviation, so 2.4 over square root of n, which is 12. So that should give you this interval. You can also just use your calculator, right? So you could have gone to your calculator. Yeah, let me just move that over just a little bit. And so you can go menu, 6, of course, 6, and T interval. And we don't have the data, we have the stats here. We don't have a list. So X bar was 30.2. Standard deviation was 2.4, I believe. And N is 12. And 95%, I think, was correct. See if we get the same 28.68. Yep. So 28.68, comma, 31.72. So we are 95% confident that the interval from blank to blank, those two things, captures Alex's true mean home to work commute time along the modified route. The follow-up question was, use that, whether you agree with Alex's concern about the new traffic lights, so have changed. So what was the mean? So his old time, I believe, was 28.4, right? If you read the question. So 28.4 was old. So it's not 0, or it's saying, does that fit in the interval? No. So we have evidence to say that the new commute time with the additional changes in the traffic flow is different. It is more, in fact. So I think we have evidence to say that. The National Endowment of Humanities sponsors summer institutes to improve skills of high school teachers of foreign languages. A simple random sample of 15 French teachers from such institutes was used to test the impact of the program on teachers' listening skills. At the beginning of the period, the teachers were given a Modern Language Association's listening test of understanding spoken French. After 4 weeks of immersion in French, in and out of class, the listening test was given again to the same people, I believe. The actual French spoken and the two tests was different, so simply taking the first test should not improve the score of the second test. I like that little disclaimer there. Table shows below the given pre-test and post-test score. The giveaway here as to why you know this is paired data, they even do the differences for you, right? It's the same person, the same 15 people are doing the pre and post. So it's all about the differences. So the only group of data, we don't need any of this. It has nothing to do with us right now. All we care about is the difference for this one, because it can be a paired t-test. Does the data provide convincing evidence at the alpha 0.05 level that the Summer Institute improves the French listening skills of teachers on average? So we're hoping for post minus pre, so we were hoping for positive numbers there. And you can see a lot of positive numbers there, so you have some evidence. Let's see what happens here. So the mu of I like to say diff there as the subscript is equal to, mu is nothing's unusual right here, right? It's just 0. But the alternate is we think the mu of the diff is going to be greater than 0. What is mu of the diff? So you're going to define that. So it would be something like the true mean difference, post-test minus pre-test, in listening test score after 4 weeks of the language immersion for all teachers that attend the institute. Okay, this is called a paired t-test. paired t-test for means, t-test for means, or for mean difference. Probably paired t-test is okay to get full credit there. So let's check the conditions. So random, I'm hoping it says random sample somewhere, or simple random sample of 15. So random sample, 15 teachers. Okay, 15 is less than 10% of all teachers, French teachers that attended the institute. So our sample size is not big enough, so we probably need to type this in our calculator. I think we do. So let's call this diff. We'll call it difference because I already had diff in there. So if I remember to do that, 2, 0, 5, 5, 3, 3, 2, 3, 0, 1, 1, negative 1, 2, 3, 3. 15, that's a good sign that I did it right, hopefully. So I'm going to graph it. And it's called difference. It's all about the diff, right? Okay, so you're going to graph that in your paper. I'm just going to check the box plot, especially for outliers. I like to do that. Good. Actually, for some reason, the box plot looks more symmetric here. So definitely no outliers and looks roughly symmetric, or at least no major skew here. So I would draw that on your paper, the graph, and say that there are no outliers and no major skew there. Good. Okay, again, you can just do this in your calculator at this point and give the t-value, t-score, and the p-value if you want to. But let's just practicing here. It's good work here. So I'm just going to do the test first. Again, this is something you might end up doing quite often on these kinds of problems. 6, 7 is tests. This would be called it's just a t-test, even though it's paired as a paired t-test. Data, we are definitely using data here, I think. So the null is 0, right? So the list is called difference. And the alternate was greater than. Okay, so if you want to do t from that, you could say x bar is 2.133 minus the mu is null, is 0, over a fraction, and that's going to be the standard deviation 1.726 or 727 over square root of 15. Should give you 4.78. Wow, that's a whopping big t-score. So expecting a very small p-value here. You could graph it. I go 0, 1, 2, 3. I'm going to put 4 there, man. So it's like way out there, like tiny little area, like so tiny. So you could use t-CDF from 4.78 to infinity and put your degrees of freedom, which in this case was 14, right? And that should give you a p-value. This is not a two-sided test. You don't have to worry about that. Point very, very small. I knew it was going to be very small, 0.0001, somewhere around there. So that's our p-value. And we have our degrees of freedom, our p-value, and our t-score. Those are the 3 things you have to have in your paper. Degrees of freedom is more of a preference for me, but I think those are 3 things you want to have on your paper. So I conclude, because the p-value is very small, it's way less than 5% at 0.0001, we reject the null. We do have convincing evidence that the true mean difference, post-test minus pre-test, in listening test score after 4 weeks of language immersion is greater than 0. We know there's a difference. So in other words, we have convincing evidence that the Summer Institute improves French listening skills. We can, we prove causation there. That's okay. And one more problem. Delphenia polcaria, whatever that is a water flea, a small crustacean that lives in lakes and is a food supply for many species of fish. When fish are present in the lake water, they release chemicals called pheromones that induce water fleas to grow long tail spines and make them more difficult for the fish to eat. One study of this phenomenon compared the relative length of tail spines in water fleas when pheromones were present and when they were not. Below are data from the tail spine lengths for the 2 random samples of water fleas taken from each population. Is there convincing evidence that the mean tail spine length of water fleas is longer in the presence of the fish pheromones? Okay, so we have some evidence that the present is, let's see, the mean seems a little larger, standard deviation is larger. Okay, so we have some evidence. Let's test this out here. So let's think it through. So we want to, so the null and the alternate. So I'm going to do present mu of the present minus mu of the absent. The null is there's no difference, right? But we think that actually there might be a difference. We think it's going to be greater than 0 because we think the present is going to be larger than the alternate there, than the absent, I guess I should say. Okay, so then you defined mu p is the true mean length of all water flea tail spines when the pheromones are there. And then mu of A is the true mean length of all water flea tail spines when the pheromones are not there or they're absent. Of course, alpha is 0.05. So we're going to do what's called a 2-sample t-test. Okay, say something about random sample maybe. 2 random samples. So random sample of 214 trees or fishes or whatever are these water fleas. And then random sample of 152 water fleas where the pheromones were absent, and the first one is where the pheromones were present. Because you see that words, and then 214 is less than 10% of all water fleas, fish with the pheromone present, and then 152 is less than 10% of all the fish when the pheromone was absent. Well, I guess it's water fleas in the lakes in which the fish, the pheromone is either there or not. Okay, so let's check the large sample. So 214 is greater than or equal to 30. That's certainly true. And 152 is greater than or equal to 30. That's certainly true. Check. So it passes the conditions. So now I might consider just doing this in your calculator at this point. So menu 6.7, I think it's a 2-sample t-test, right? This one is not data, it's stats. X bar 1, I think we're doing that 37.26. 4.68, 214, 30.67, 4.19, 152. And the alternate was greater than here. It's always helps to have done that first. So now we know that, well, we know the t-value, but let's just figure it out. So let's plug into the formula. So it'd be 37.26 minus 30.67. You could say minus 0 there if you want. So this is over 214, this is over 152, 4.68 squared, and 4.19 squared. So t is 14.11. Oh my goodness, this is gonna be a small p-value. I mean, how are you gonna graph that? Like 0, 1, 2, 3, like way out here, there's like a tiny little area, like, oh my goodness. So you're gonna do TCDF 14.11 comma infinity comma degrees of freedom is 345.08, right? Oops. And so your p-value ends up equaling so close to 0, we're just going to say approximately 0. That's okay to say. It's probably a scientific notation number there. So we have to have that. We have to have that. Really good to have degrees of freedom labeled somewhere in your paper. Because the p-value is so tiny, it's way less than 5%, we reject the null. We have convincing evidence that the mean length of water flea tail spines when fish pheromones are present is longer than when pheromones are absent. So we have proof causation there, at least for fish like these. Okay, that's your lesson for today.